Howdy. I thought I would do a little bit of backtracking for some basic fundamentals that we've got to really understand before we can understand the rest of the module. Otherwise, things get a little murky. Last night we used a coil, if you remember, and we put a magnet in the proximity of the coil, and we saw some interactions with the telephone. Well, let's look at what Faraday discovered back in the 1830s that really underwrites all these principles. So here we have a meter that detects electrical flow. If the needle moves, then we know there's electrical current being produced. And here I have a coil. This is a little more elaborate coil. It's many more wraps and smaller wires. And we'll speak to that in just a second. But this will give us a little more demonstrative effect. This will also work with a coil that we used last night, but not as demonstrably. So here's my magnet again. This is my rare earth magnet. And I'm going to bring this into the proximity of the coil. And you'll see that when the coil is at rest and there's no magnetic field, there's no current. When the magnet comes into view, there's a current. And when it leaves, there's a current. But notice, when the magnet is stationary, there's no current. So in our humbug experiment where we saw the magnet resting on the two spark plugs next to the coil, there is no physical, theoretical reason why there would be any current flow. Now also notice this, that when I move it quickly, the needle jumps faster and it jumps further. So if I get it close and I jerk it, we get more electricity. The principle of this is that the magnetic lines of field, or magnetic lines of force, cut across these coils, cut across the actual copper wire, and in the copper itself, those magnetic lines urge electrons to move. And the faster the lines move, the more urging that there is. And we call that urging EMF, or electromagnetic force, or generating a voltage. So a moving magnetic field, or if we have a magnetic field that is stationary, we can move the coil. Let's see if I can do that without losing the video here. I'm going to move the coil back and forth. We see the same thing happens. So we can either have a moving coil or a moving magnet. It doesn't matter, just so long as those electromagnetic lines keep moving. So the whole principle of generating an electrical field or generating an electrical force requires a moving magnet or moving magnetic field around a conductor. And so if you have more conductors, if you have more copper lines, then there's more opportunity for the magnetic field to cut across it. So you have more generation of electricity. So when we look at generators, and here's a generator. I'm going to switch fields here now. Here we have inside really a little generator, and we have two magnets, one magnet on one side, one magnet on the other. If you notice on the inside, there's lots of little coils of wire. So when the generator moves like this, the coils actually are the ones that move within the magnetic field, because there's a magnetic field that goes across here. So it actually generates electricity by moving inside that magnetic field. If you take it apart, you can see what's going on here. Inside there is the coils of wire around, and then we collect it on something called a commutator here, which is a couple of little copper pieces where the electricity will be collected. But inside there are two big permanent magnets. So in that respect, we can generate electricity, and you can demonstrate this effect with a generator by just taking a simple little motor. And that's really all we had right here. It's a motor, but it's also a generator if we generate electricity by moving the motor in the magnetic field. So I have, and you have in your kit, a little motor and a little LED and a light emitting diode, and I connected the motor to the light emitting diode. And if I rotate the motor, you notice I have to rotate it one particular way. If I rotate the motor, you can see a flash on the LED. So what's happening is we're moving the wires, cutting across the fixed magnetic field, producing an electrical current which will light the LED. I could also attach this to the meter and figure out how much electricity I'm creating. So again, it requires movement. So in a wind generator, this is attached to a propeller through gear system, and it moves magnets inside or moves wires inside a magnetic field, generating electricity. So it has to be moving. Same thing with a hydroelectric plant. This is attached to a turbine where the water goes through, it moves the turbine, and the turbine moves the generator and generates electricity. So most all electricity that we have comes from this system where we're actually moving a shaft, like the one in Boardman there. That shaft is moved by a jet engine. And the jet engine is turned by gas, natural gas. The jet engine moves a shaft, and the shaft moves a generator, and the generator generates electricity. So we have one kind of energy, natural gas energy, which is converted into heat. The heat is converted into a gas which pushes this impeller or turbine. The turbine then is a mechanical energy that goes into here. Mechanical energy then is turned into electromagnetic force and lines of field, which are then converted into electricity. So we have lots of energy transformations. But the basic fundamental is a moving magnetic field is what's required for all of these energy conversions. And if we don't have a moving magnetic field, then we don't have any generation. Now notice too that this takes quite a bit of effort just to get a little energy going. So the experiment that we saw, or the humbug that we saw on the screen, could not possibly work because the coil was so small. Even if you did put a magnet near it, you would get probably very little jump on a tiny little sensitive meter like this. All right, so I'm going to add this to the Canvas and to the website. Hopefully that helps a little bit. If you have any questions, please shoot me an email. Bye-bye.